First thing is, if you're the last person to use the hot plate, make sure you switch it off. Otherwise, it could pose a danger. But that's not so bad. Spilling stuff all over the place. Right? This I don't mind so much, but this I don't really like to see. In fact, this is the person or persons doing this need to seriously improve their technique, or they shouldn't be handling chemicals. Basically, don't let them handle.
Is that our class?
Yes.
Oh, it is.
Right. Yeah, this is just too much. Too much. It's the worst I've seen in Chem 1B. Normally, that's why I don't really look there, but and this, at least clean it up so I don't have to see it. Otherwise I'm going to have to rethink how I do the lab.
Virtual lab?
No, not virtual lab. Lab technique is an important part, lab safety and techniques. And actually, there is an official rule. People who can't do the lab safely without endangering the health of the other students can be kicked out of lab. But it's never been applied. But something like this, although that's oxalic, but something like the dichromate and spilling it all over and not cleaning it up is posing a health risk to other students, which is not good. And so, make sure you clean it up. Not only that, dichromate's a powerful oxidizer. There's a metal that's going to corrode it, too. And so, hopefully I don't see this anymore. Otherwise, we're going to have some kind of sign out or something. This is still here in hood number 1, but this happened in the morning, and I made them clean it up. Just get some gloves, wet paper towel, wipe it up, throw it in the garbage. But nobody cleaned this one up, so somebody should clean this up. So just be more careful, when you do this. I don't want to resort to having to watch every single person or have them do a sign-in sheet. I used to do balanced sign-in sheets for Chem 4 and Chem 1A, but never for Chem 1B, where I just have a personal record and I can see if they left the balance dirty or clean. So that's safety. Let's talk about this lab that we just finished today. We have some time. Before I start talking about this lab, let me just get in sync with the other class here and just start one calculation. I want to start the calculations just so you have some idea about this method before the weekend. And that is when we looked at 1.00 or 1.0 times 10 to the minus 8 molar. 1.0 times 10 to the minus 8 molar. Ammonia? Yeah. Okay. So the setup is the same as before. Step 1, we'll do the biggest K. The biggest K is going to be KB. KB for this was 1.8 times 10 to the minus 5. And so we'll start with that. We have ammonia hydrolyzes water to form ammonium and hydroxide. In the previous problem, what was the percent hydrolysis that we saw? About 1.34, 1.33% hydrolysis. In this problem, are we going to see the same amount of hydrolysis? No, because the initial concentration is different. And therefore, we can't just do a simple percent calculation. It's always this percent reaction. We actually have to sit there and calculate it using an ice table. And so we'll have 1.8 times 10 to the minus 5 molar. What do we do with H2O liquid? Ignore it. Ammonium, 0, and hydroxide, 0. So we assume none of the molecules have hydrolyzed yet, which is fine because we can approach equilibrium from any direction. And then we have our minus x molar, plus x molar, plus x molar. And then our 1.8 times 10 to the minus 5 minus x, and x molar. Okay. Now, did anybody solve this one?
Yeah.
Okay, did you have to use the quadratic or did the simplifying assumption work?
Quadratic.
The quadratic. The simplifying assumption fail?
Yeah.
Okay. That's correct. The simplifying assumption is worth a try, but it will fail in this case. And we get x squared over 1.8 times 10 to the minus 5 minus x. We can just write a little note here. SA fails. And then we go for the quadratic, and we get it in quadratic form. X squared.
Isn't it 1.0 times 10 to the negative 8?
Oops. Yeah, right. 1.0 times 10 to the negative 8.
In the I system.
I was looking at my KB. Sorry. That's correct. 1.0 times 10 to the negative 8. So we get x squared plus 1.8 times 10 to the minus 5x, and then 10 to the minus 8 times 10 to the minus 5 gives me minus 1.8 times 10 to the negative 13 is equal to 0. And so what did you get for your x?
9.994 times 10 to the negative 9.
Right. And so here, we start off with 1.0 times 10 to the minus 8. I'm going to write in decimal form. So that means I need 7 zeros. 1, 2, 3, 4, 5, 6, 7, and then a 1, 0. Okay, minus 9.9 times 10 to the minus 9, so I'll need 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros, and then a 9, 9, 4. And so in this case, how much did I lose? You know, in the last case, it was 1.34% reaction. In this case, how much reaction was there? So if I started off with 100 and I lose 99.4, that's 99.4% reaction or hydrolysis. And so do you see that the percent hydrolysis varies dramatically depending on the initial concentration. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then what is the number? 9 zeros and then a 1, 6. Is that what you got? In other words, I would get 1.6 times 10 to the minus 6, 7, 8, 9, 10 times 10 to the minus 10 molar. Is that what you guys got? Or not? Oh, well, we'll soon find out. 9.94 times 10 to the minus 9 molar. And 9.94 times 10 to the minus 9 molar here. When I multiply these out, what do I get for my K value? 6.17 times 10 to the negative 7. Is that what you get? So clearly I made a mistake, right? Because if I compare this K with the actual K, it's way off. And so let's try to find where the mistake was made. Maybe I got the decimal wrong. So this is 10 to the minus 8. So 1, 2, 3, 4, 5, 6, 7, 8. That's right. That's 9.94 times 10 to the minus 9. So move it 9 places. 1, 2, 3, 4, 5, 6, 7, 8. Oops. I see a mistake here I made. You see? The mistake I made was it isn't 99.4% reaction. There should have been one more 0 here. Like that. And so 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And then a 9. My zeros are offset. Let me rewrite this so a little more. 994.
Wait, 9.94 times 10 to the negative 9 is not 8 zeros? It should be 8 zeros. Yeah.
Oh, you're right. 8 zeros. Why was I thinking 9? 1, 2, 3, 4, 5, 6, 7, 8. I guess it was right. I was right. 99.4% reaction. And so is this right? This should have 9 zeros, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And so it comes out to 1.6 times 10 minus 10.
I got 5.6 times 10 to the negative 12.
Yeah, I got that.
5.6 times 10 to the negative 12?
Yes.
Oh, I didn't get that.
I got 6 times 10 to the negative 12.
Oh, you know what? I miscalculated. If it were 98.4, you're right. It depends on how many digits you carry in your calculator. This should have been 0.6. Sorry. 0. So we're just 6/10 of the way to 100. If you carried more digits in your calculator, then you're going to have a different number here. Was this number rounded, 994? Was the 4 rounded?
No.
No? Okay, that's good. All right. Now let's try it again. 0.6, even though that's only 1, you probably would want to carry more digits here, but let's go ahead and just try 1. 0.6, and then repeat the calculation.
$1.646.
1.646
Yeah, that's 10 to the negative 6.
times 10 to the negative 6.
Yeah.
Still way off, huh? Still way off. So is that due to round off or is that due to calculation error? Let's see. Can somebody recheck X here?
Yeah, it's supposed to be 9.994.
9.994?
Yeah.
Okay, so I probably wrote it down wrong. 9.994. .994. So let's just carry 1 extra and see if that's enough here. And so I'm just going to call this 9.99 times 10 to the minus 9, 9.99 times 10 to the minus 9, and let's redo this. 9.99 times 10 to the minus 9 is going to give us 1 here. It's only one sig, that's not even officially sig fig, but it's only one digit. One digit usually means severe round off, right? And so this is a case where you might carry extra digits so you don't end up with one digit. All right, so what does it come out to this time?
I got the same answer except the negative fifth.
1.64 times 10 to the negative fifth. And so this brings up the question, you know, did we make a mistake or is it because of round off? And so what we need to do here is we need to carry extra digits to C. And this is due to rounding off too severely. And so let's go ahead and carry extra digits here to try to compare with the K value, the accepted K value. And so, Jameson, what did you get out in your calculator?
9.9944.
Anything else?
506.
506. All right, times 10 to the minus 9?
Yeah.
All right. So this is what we're going to do. We're going to use all the digits there. 9.99445506 times 10 to the minus 9. Instead, here and here. This way we're going to minimize round off error by dropping digits. And then over here we're going to redo this calculation carrying that many digits to see if we could get a better answer and thus determine, well, it was due to round off that we're so far off. So let's go ahead and do that. But, you know, in this case, let's just punch it in your calculator. 1.0 times 10 to the minus 8 minus 9.999. Since we are going to ignore sig figs for right now and just carry as many digits as possible, what does this come out to? 5.549. 48. 5.549.
Another
4.
four. Times 10 to the negative 12.
Is that it? 0, 0, 0?
Yeah, that's not right.
Nothing after that? Times 10 to the minus 12. All right, now recalculate K and see what you get.
1.79 times 10 to the negative 5.
Okay, so now K comes out 1.79 times 10 to the minus 5. How does that look?
Pretty solid.
That looks great, right? But what do we do with our answer? Do we carry all the, are we allowed that many digits?
Yeah.
We aren't. But at least what we know is we know that it was due to round off error and not calculation error, our problem. And so what we'll do is we'll just go ahead and round this. I mean, if we were to round this, this would round to 10, right? Times 10 to the minus 9, 10.0. But we aren't going to round it. We'll carry one extra digit. So this is going to be 9.979, 9.979. This was just to eliminate the possibility of round off error, and then we just round this. This would be, 5 or 6. Actually, I had 6 times 10 to the minus 12 originally, right? But that was too much round off, huh? Does that make sense? Okay. Good. All right, now we have to ask ourselves this question, and that is, will water be a significant contributor to hydroxide or an insignificant contributor to hydroxide? What do you think? A significant contributor, and the reason I think so is because of the small concentration. This is 10 to the minus 9. If we only have 10 to the minus 9, then it's going to be a significant contributor, isn't it? Yeah. And so that means we should factor in the next step. The next step would be KW. And so let's do that over here. Step 2. Step 2, I have H2O liquid plus H2O liquid goes to H3O plus OH minus. Water we ignore. And so initial hydronium is what?
Oh,
0. We assume no water has reacted yet. And hydroxide? 9.99 times 10 to the minus 9 molar. And then the change is going to be plus X molar, plus X molar. And so at equilibrium, I'm going to get X molar and 9.99 times 10 to the minus 9 plus X molar. All right, now, do you think the simplifying assumption might work in this case? Kw is going to equal the hydronium ion concentration times the hydroxide ion concentration. And that's equal to X times 9.99 times 10 to the minus 9 plus X. You could try it because it doesn't take very long, right? If you just drop this X, then it's going to be 10 to the minus 14 divided by 10 to the minus 9. You know, just as a rough ballpark calculation. If we were to do the simplifying assumption, we'd assume that X is small here, drop that. And so we get 10 to the minus 14 divided by, actually this would be 10 to the minus 8. Well, we'll leave it at 10 to the minus 9, just ballpark. That would give us 10 to the minus 5, right? Minus 14 plus 9 is 5. 10 to the minus 5, is that small compared to 10 to the minus 9 or big compared to 10 to the minus 9? It's huge. And so the simplifying assumption would definitely fail. And we kind of expected it because we were asking ourselves, should water contribute? Yeah, we expect it to contribute significantly. Now, how much does it contribute? Doesn't water contribute 10 to the minus 7 molar hydronium and 10 to the minus 7 molar hydroxide? No, why not?
We have a concentration of OH.
Yeah, we have a concentration OH minus. You know, you could use that predator analogy, or we could use Le Chatelier's principle. Le Chatelier's principle says if you build up the product, it's going to be wanting to shift this way, but it can't shift this way because this is 0. We have to build up a small concentration of this. So this we call Le Chatelier's kind of inhibition of the forward reaction. Having a lot of product there inhibits the forward reaction from fully occurring. So we need to use the quadratic, and X is equal to, should we get it in the quadratic form? That would be X squared plus 9.99 times 10 to the minus 9x minus 1.0 times 10 to the minus 14 is equal to 0. And so use your quadratic solver and then solve for x, and you get what?
9.512 times 10 to the negative 8.
9.51 times 10 to the negative 8. We'll just carry one extra, which is the same thing as 95.1 times 10 to the minus 9, right? And so going over here, did we add a lot? I'd say, I mean, we started with 9.99 times 10 to the minus 9, and we're adding 95.1 times 10 to the minus 9. You see we're adding a huge amount of additional hydroxide here. And so we're going to end up with, what? 9, 10, 15, 105. 105.09 times 10 to the minus 9 molar. And then over here, X is just 95.1 times 10 to the minus 9 molar. Let's just make sure it double checks. With these two equilibrium concentrations, what is our K value equal to? So can someone just double check to make sure I didn't make any errors? What does the K come out to?
.98 times 10 to the negative 15, right?
All right, 9.98 times 10 to the minus 15, which would be 0.998 times 10 to the minus 14. If you were to round this to 2 sig figs, what would it round to? If you round that to 2 sig figs, you'd bump this up and then it'd round to 1.0 times 10 to the minus 14, which is good, right? That's what it's supposed to be at equilibrium. So does this look good so far? Yes? Except there's one major problem here. I don't know if you can see it. Do you see a major problem? The one major problem is this. If we go back to step 1, remember we calculated the K value. The K value took some time to figure out. Oops, that's not it. It took some time to figure out. This is it. But the K value finally came out to 1.79 times 10 to the minus 5, right? We make sure, because the equilibrium concentrations, when plugged into this equation, should equal 1.8 times 10 to the minus 5, right? And that's with a hydroxide ion concentration of 9.99 times 10 to the minus 9. How much extra hydroxide did we just add to it? We started with about 10, and we added about 95 parts, right? So we added about 95% of the new total is from water. And so our new hydroxide concentration is 105. 105 is our new hydroxide concentration. Our original hydroxide concentration was 9.9. The problem is this new hydroxide concentration, right, going to upset the equilibrium I had just established over here? In other words, what does Le Chatelier's principle say? Le Chatelier's principle says if we take a system at equilibrium and then we dump in more product here, we're going to expect a shift. And so you know what I have to do now is I have to do a step 3. My step 3 is I need to take my new hydroxide, plug it in here, and then figure out how much it shifts to the left. And so I should do step 3 because now step 1 is all screwed up. Do you see that? But if I do a step 3 and figure out my new hydroxide, what's that going to do to step 1? Not step 1, step 2. It's going to mess up step 2. And so do you see we're in an impossible situation where we're going in circles because once we fix one, the other one's out of whack, and then we fix that, and then do you see that? And we're in this endless loop where we're never going to get out of it. And so how do we solve this problem? Because we cannot solve this problem doing it in steps because each step screws up the previous step. This is different than the earlier problems. You know, see why in this case it's different. And so we need another technique for solving this, which we're going to talk about later. And so this is just something to think about now. So we'll revisit this problem next week. All right, next week we're also starting a new lab. On Tuesday, we have the test. And so on Tuesday, I think what I'm going to do Tuesday is just a lecture for the first half and then test for the second half. Thursday we'll start the actual lab. So Tuesday I'll probably lecture about what the lab is all about. But let me tell you what the lab is. It's going to be a multi-day lab. I think 5 lab periods, maybe 6. And the topic is qualitative analysis. Qualitative analysis is trying to figure out, what ions you have in solution by using simple chemical tests. And so you're going to get an unknown solution, i.e. there's ions in there, but you don't know what ions are in there. And then you're going to run some chemical reactions to figure out what ions are actually present in that solution. The way the lab is going to work is initially you're going to do it in groups. And so what you're going to do is you're going to run something called the known. The known has all the ions. There are 10 possible ions. It has all of them in there. And so when you run your known, you should be getting reaction at every step. That you're supposed to be getting reaction. You should just see what it looks like, in its entirety. After you run the known, and so you kind of have an idea of what the whole experiment is about, you'll run an unknown. The unknown isn't going to have all the ions, likely. I'm not going to give you the exact number of ions in there, but it's anywhere from 1 to 10. Unlikely it's going to be full 10, but what that means is if you're missing ions in there, will the same procedure work? And so this is where the whole concept of what makes a good student is a little bit different. What makes a good student is not hitting at 10 milliliters of ethanol. What makes a good student is they know what the ethanol is there to do. The ethanol is to maximize the precipitation, right, the crystallization. And so you keep adding it until you've maximized it. Well, the same thing goes in qualitative analysis. In qualitative analysis, if you're adding a reagent for precipitation and nothing's happening, right, you just keep adding more until you're absolutely sure nothing's going to happen. But you don't stop at where they say to stop. And so sometimes you have to add much more reagent than what the experiment calls out for. The people who follow the procedure exactly as written aren't going to get good results because you have to modify it on the go. The same thing happens when you add a reagent to dissolve a precipitate. Let's say they say dissolve the precipitate in 5 milliliters of concentrated ammonia, but when you add the first drop, it's gone. It's all dissolved. Are you going to add the remaining drops? No, you wouldn't add the remaining 100 drops or 99 drops because it's already dissolved and you've accomplished what you set out to do. And in fact, if you add the remaining 99 drops, you know what's going to happen? It's going to get overly dilute and overly concentrated in ammonia, which screws up all the subsequent steps. And so you're constantly adjusting the quantities, either lower or higher, depending on what you're trying to accomplish. And so the way you think about the experiment is different. The way you think about the experiment is, I don't mix this many mils with that many mils. The way you think about it is, I'm trying to precipitate out this compound at this step, and therefore I need to maximize the amount of precipitate. Or I'm trying to dissolve this compound at this step. And so you try to dissolve it in a minimum with stirring. That way you don't you don't hurt yourself by adding too much, or too little in case of precipitation. And so those are things we think about in this next series of reactions. Well, that's a long experiment. This is also a tough experiment, the synthesis one, because this one is going to have a formal report that you need to turn in. And the formal report, well, on the one hand, it won't be too bad because you can turn in a group report. That is, you can work with your partners as co-authors and then just write the paper together, rather than an individual report. In the past, I've done this experiment individually, but this, with enrollment crunch, I've been adding extra people, and it's getting harder and harder to work individually. But let's talk about the formal report right now. The most important section of the formal report is something we call the discussion. And this is where most of the points are going to be wrapped up in. So this is what you really want to think about when you're thinking, because this is going to be the toughest thing to write. The toughest thing to write is, what's happening in this experiment, at a chemical level, at a deep level. In other words, you want to describe what's going on in the experiment, and you don't describe it saying, I mixed 10 mils of this with 15 mils of that. Those are called experimental details or experimental procedure. That's written in a separate section. In this, you're saying you're mixing this with that to accomplish this, right? And so it's a little different. We don't care about the amounts. We're just looking at what we're trying to accomplish. And so what was the first step? And so let's take a look. We'll just outline it. It's going to be in paragraph form, so you don't leave it in outline form. But, what were some of the key things that we did in this? Actually, what did we do? What we did is called a synthesis, that is making a compound. And normally this type of paper, this type of formal report, is called synthesis and characterization. Blank, whatever you're trying to synthesize. And so there are lots of synthesis and characterization papers out there. It's just a standard format that you see. Synthesis is just making it, but what is characterization? Characterization just means characterizing the product. In other words, you're analyzing the product. So for example, the oxalic acid. The oxalic acid, do you remember what percentage it was? The oxalic acid monohydrate that we're using is 98% pure. That's a characterization. It's 98%. It's not, that's called technical grade oxalic acid. There are higher purities available. You could buy 99.999%. It's going to cost you more money, but it's a lot purer. And then if we go on the internet, we can see the spec sheet on the oxalic acid. It has this percentage of this impurity, this percentage of this impurity, etc. That's characterization. So how pure are your crystals? Are your crystals 100% pure? Or how do you know how pure they are? That could do it, but we try to get rid of, even if we're using impure oxalic acid, 98%, we're assuming the 2% stays in the solution and is now sitting in that waste container in the back there, the 2% of impurities. And so hopefully our stuff is very pure, but how pure? And this is what happens in science. Somebody's not going to take your word for it. You say, I got some nice crystals of potassium trioxylatochromate 3, trihydrate. But, they're going to say, well, how do you know that's what you synthesized and how pure is it? How do you know? Because even looking around, I see different colors. I see light-colored crystals, I see dark crystals. Are the light-colored crystals the pure stuff or the dark-colored crystals the pure stuff? Okay. How do you know? Are the bigger crystals the pure stuff or the little crystals the pure stuff? And so this is an important part, but when you read our lab, does our lab, the title of this lab say synthesis and characterization? No, the title of this lab says, preparation, which is synthesis, and reactions, which is synthesis. Synthesis and synthesis of this. But where's the characterization part? And so this is something you got to realize, and a lot of people think, like in a formal scientific paper, a conclusion is just a summary. No, in most scientific papers, a conclusion isn't a summary. A conclusion talks about the limitations of the study. Conclusions talk about if you had more time and more money, what would you have done? conclusions talk about the weaknesses of this. And so, anyway, what we'll talk about is one of the things that helps us understand purity is this. Usually big crystals are more pure than little crystals, because in order for a crystal to grow big, everything has to fit into place. And so if an impurity comes along, the impurity is usually bigger or smaller, and it disrupts the crystal lattice, preventing it from growing nice and perfectly. Right? And so people usually like big crystals. Like if you look at the semiconductor chips are printed on single crystals of silicon. And that silicon, they do a process that's called recrystallization. What they do is they keep crystallizing it and then melting it, crystallizing it and melting it. And each time they're doing this, they're removing more and more impurities. You could have done one recrystallization and gotten more pure crystals. You know what you do? What you do is you generated your crystals, and then you go, great. You got rid of most of the impurities into the waste there. You washed off the rest of the impurities, right? And so the next step is dissolve the crystals you have and then recrystallize them. And so when you dissolve it, there could have been trapped impurities in there. You dissolve it, you break it apart again, and then you recrystallize it. When you recrystallize it, it removes more impurities, because as it crystallizes, and hopefully it crystallizes slowly. Crystallization, and some people got tiny crystals, some people got big crystals. It depends. It depends on a lot of factors, because crystallization, there are two main processes. There's nucleation of crystals. That is, you have to nucleate them or start them, and usually you start them on cracks or scratches or dirt particles, dust particles, where the ions can stick. And as the ions stick, new ions come and attach to that. And so normally, if you're trying to grow nice big crystals, you do it in very clean glassware. You don't introduce a stir rod in there or the spatula, because that provides nucleation sites. And you just try to minimize the nucleation. So if you only nucleate 3 crystals, then those 3 crystals are going to grow huge, right? But if you nucleate 1,000 crystals, they're never going to grow very big. And so you want to nucleate a minimum of crystals and have those grow big, hopefully excluding out the impurities. And so we like to see are nice big crystals. The next thing we like is we like to characterize the solid. Now, if you think, how can you test the impurities? For example, if somebody gave you a glass of water and said, here, drink this, and you weren't sure if it was pure water or not, what would you do to test it? How could you test it? You could test the pH. If it's pH 1, I wouldn't drink it, but if it's pH 7, I'd drink it, right? You could do what? But pH isn't enough, because other things that are toxic have pH 7. What else? Boiling point. If it boils at 100 degrees C, that's good. So pH 7 boils at 100 degrees C, that's 2. What else could you do? Well, maybe there's other stuff that's toxic that boils at 100 degrees C and has a pH 7. So you would? Test its freezing point. Freezes at 0. And the more of those that you do, the more confidence you have, oh, this is probably just water, I'm going to drink it, right? Well, what about your crystals? What can you do to your crystals to test? The purity. Check the color. Good. What else?
Check the weight, maybe?
Not the weight, the density. Like, for example, gold. If somebody were trying to sell you gold and it came out at the density of 8 grams per cubic centimeter, then that's not gold. That's fool's gold, right? So you wouldn't do that. So you could check the density. What else could you do? The hardness, the crystal, the form, the shape of the crystal. What else? Hannah, did you say? Melting point. Melting point is probably one of the quickest and the easiest. In organic chemistry, a lot of organic crystals are low melting. And so you could rapidly melt them and see what the melting point is and compare it to the known melting point. The melting point is good because it gives you additional information. You know, if there are impurities in there, those impurities disrupt the bonding. If the bonding's disrupted, then you're going to have a range of bond energies. That is, they're going to be weakened bonds and strong bonds. Whereas if the crystal lattice is perfect, there are no impurities incorporated, all the bonds are the same. And so in a very pure crystal, what you have is what's called a sharp melting point. You hit the melting point and it rapidly melts the whole thing. Boom, it's melted. But in pure crystals, what happens is you start to melt it, and so you're breaking the weaker bonds, and then you have to heat it more and break the medium, and heat it more to break the stronger bonds. And so what impure crystals show is a very wide melting point range. And so in organic, you always record the melting point and the range. Sharp range, pure. Wide range, impure. And so those are things that you can do. There are other things you can do, like spectroscopy. You guys remember spectroscopy? Take a spectrum of it and then see by shining different kinds of light on there and seeing what types of things are in it. And so methods of characterization. Unfortunately, characterization wasn't part of this lab, but we can talk about it in our report, right? The next thing we can do is, well, that's probably going to be towards the end. The first thing we've got to do in the discussion is talk about the reactions. And this is a synthesis, so we need to talk about the chemical reactions. And what chemical reactions did we see? For example, we had potassium dichromate that we needed to convert to. We had potassium dichromate that we needed to convert to chromium 3 ion. How did we do that? We used a reducing agent, oxalic acid. And so the question comes up, why did you use oxalic acid? Why didn't you use some other reducing agent? And so what was the reasoning behind using oxalic acid? Could we have used any other reducing agent? Maybe like ethanol? We're adding ethanol anyway. Eventually. Was the ethanol added as a reducing agent? No, we got to talk about why the ethanol was added. And so why oxalic acid? Yeah, if you're going to characterize it, it's a better oxidizer than it is a reducer. And so why are we using such a poor reducer? Why we have the skeleton redox. Remember the skeleton redox? We have dichromate, oxalic acid. Oxalic acid here is the reducer, dichromate's the oxidizer. This is going to produce chromium 3, which we want, and how do we know it's chromium 3? You know, how do you know it's chromium 3? Because somebody else said so? Does that really hold up? You know, if you're presenting this to a group of scientists and they're very critical, will that hold up? No. Well, ask the author of the paper. No. So how do you know? Well, dichromate's what color? Orange. What is chromium 3? What color do you think chromium 3 is? No, it's not. Well, that's something you can look up later. Anyway, and then we form CO2. CO2 is a clear, colorless gas. We should know that. And so this is the first reaction. We need to balance this, remember? And did you guys balance this already? That's part of your report. And so we had this reaction, the redox reaction, right? And so why did we use oxalic acid? Well, I told you the last time. The reason is it's weak. Otherwise, if we added ethanol, what could we expect? Explosion. And so we want weak. And the other thing is, these reactions, are they stoichiometric? We add the perfect amount of oxalic acid to react with all our dichromate. Did you measure it that carefully? No, we have excess reagent, right? Which one is the excess reagent? Oxalic acid. Normally with excess reagents are impurities that contaminate our product. And these excess reagents, we have to make sure we get rid of them. But oxalic acid is okay because we need that in the next step. I mean, whether it's oxalic acid or potassium oxalate, both have oxalate. And so what is the next step? The next step is
Heating it.
well, no, we don't care about a lot of the little details. We could say heating it, but essentially we need the chromium-3 to react with potassium oxalate, with oxalate. How many oxalates do we want? 3 to form trioxalato chromate. What kind of reaction is this? Lewis acid base. And then finally, we need to crystallize this, right? Because we don't just form the ions. What do we want to form? This is like a physical process here. Okay. What are we trying to form here? What's our final product? Our final product is K3 CrC2O4 3.3 H2O solid. We need a precipitate, right? We need a precipitate. And so to get this precipitate, I need 3 potassiums and 1 trioxalato chromate and 3 waters. There's lots of waters around to get this. And so we have this final step. Now, how do we accomplish this? How do we accomplish the precipitation? Well, we added ethanol. What does the ethanol do? Well, ethanol and water are interesting because ethanol and water are miscible in each other. Do you know what miscible means? Miscible means that they mix in all proportions. An analogous thing, in other words, this is what we call an ideal solution back in chapter 13. And normally in Chem 1A, I show this. Of what an ideal solution is. Water and water, will that form an ideal solution? If I mix water and water? Yeah, it's ridiculous, right? Water and water is going to form a water mixture. But they mix ideally. They mix ideally in the sense that miscible are infinitely soluble. Is there any limit to how much water I can add to water? Or is there a solubility limit? There's no limit. And so the same thing happens. If I have ethanol and water are infinitely soluble in each other. I can add any amount of water to ethanol, or I could add any amount of ethanol to water. Does that make sense? And so this is why when somebody asks me about adding the ethanol, I said, go ahead and add it, because what are we trying to do at this step? Well, it must mean that this compound is soluble in water, but must be insoluble in ethanol. And so all we're doing here in this step is we have water, and the more ethanol we add, the more ethanol-like this solution is. In fact, pretty soon we'd stop calling it an aqueous solution and we'd start calling it a ethanol solution. And so what happens is eventually you have so much ethanol that there's only a tiny bit of water and it's all ethanol. And so what we've just done is converted it from an aqueous to an ethanol solution. And when that happens, this stuff should fall out. I don't know how soluble it is. It's probably not 100% insoluble. But it's okay if we lose some because we don't have to get all of it. And so we have this last step here, the crystallization step. Now, let me do this. Do you want to take a break or finish a little bit early? Finish early? Okay. Unfortunately, I was having problems with this morning too. Not wanting to work. All right, it finally worked. So let me give you some examples of reports from the past. These are going to be different because these reports were individual reports. Like I said, I like to do this lab individual rather than in groups. And so I made everybody write their own report. And so since yours are going to be group reports, the standard is going to be a little bit different. Maybe a little, since the workload is a little bit less. And so anyway, there are different parts of the report. There's an abstract here, an introduction, experimental section, and a results and discussion section. At the end, there's a little reference. This person didn't put a reference section. So the results in discussion or the discussion section will be the most important part of the report. Let's take a look at some more of these. Here. This is the problem. This cable is bad. All right. The same thing, abstract, etc. And so let's take a look at some abstracts and then see or get an idea of what you need to do. Maybe it's not going to work for me today. Well, how about this? We're going to have the quiz. Well, since this is not working so well here, let me just tell you about the report. In the discussion part of the report, you're trying to explain, why you think you got what you got. The reactions that you took, doing this procedure, the washings. Everything's going to lead you to believe you synthesize what you synthesize. You want me to read it to you? All right, if this one stays on, then we'll look at this. If this doesn't, then I give up. Okay, let me just, I'm not going to disturb the cable at all. All right, so let's talk about abstracts. About 90% of the people that read your paper will only read the abstract. Most of the time when you're reading scientific literature, like me, I've read hundreds and hundreds of abstracts, but I haven't read hundreds and hundreds of papers because not all the papers are that significant to what I'm working on, or if it is, then I'll read the whole thing. And so the whole purpose of the abstract is to give a one-paragraph synopsis of what you did and what you found. And so essentially, it's a spoiler. You don't want to wait until the end to tell. You just tell them the final result in the abstract. That way, nobody has to read the whole paper. And so this, when we look at it, what you did and what you got. And so here, a coordination compound is made up of a central metal ion to which other ligands are attached with. In the oxalate complex of potassium trisoxalate, chromate 3 trihydrate, the oxalate acts as a Lewis base by donating the free electrons in its structure to the metal, that is the Lewis acid. For the preparation of this complex, the strong oxidizer dichromate. Let me just finish reading that. Reacts violently with oxalic acid. After the addition of the compound potassium oxalate monohydrate, the mixture slowly produces deep blue crystals once it is cooled. That's one abstract. Another abstract is this. This one I like a little better. The purpose of this experiment was to understand coordination compounds. K3Cr C2O43.3H2O was created in the lab through chemical reaction and filtration. The reaction was made up of Lewis acid base, redox, and metathesis. Was there a metathesis reaction? I know there was redox, there was acid base, but was there a metathesis reaction too? And the answer is yes, there was a metathesis. This metathesis reaction didn't occur in water because these ions in water would stay in water. But when you change the solvent to ethanol, then all of a sudden the ions prefer to be with each other rather than in ethanol. And so this is a metathesis where they wouldn't come together in water, but they will come together in ethanol. Potassium dichromate, oxalic acid, and potassium oxalate monohydrate were used in the process of making K3, etc., along with an intermediary step of filtration and ethanol wash. The resulting acid-base reaction was a combination of rock-like and sand-like dark blue chunks of crystals which were purified and weighed out. And so that's another one. You could add more to it. No, you wouldn't necessarily want to add less. But this one is too much. Listen to this abstract. You know, the first thing is they give the equation that's copied from the book. The equation that's copied from the book is just the two equations added up. Here. 3 equations added up. I like to keep it separate. Preparation of oxalate-containing coordination compound was the goal of the experiment. To a suspension of oxalic acid in 20 milliliters of distilled water, potassium dichromate was added slowly. Somebody who's reading the abstract, do they want all those details? No, they just want you to get to the point because they don't want to waste a lot of time reading. Unless they're interested in making it. If they're interested in making it, then they can read the whole paper and see how you made it. The numbers like that are going to come in the experimental section. In the experimental, you'll say, I mixed, or 3.6 grams of this was mixed with that, etc. In the discussion section, you're going to talk about, what the role of each reagent was and what the role of each step accomplished or did or whatever. Okay? And so we'll talk about this more. Unless, did you want to see a discussion section?
Yeah.
Okay. Let's look. Oh, gosh. I shouldn't have touched this. I think this jack is bad.
Blow it out. Now blow it out, return the cartridge.
Okay, maybe that.
No way, that worked.
It's supposed to.
It's working.
Secured everything. Taken.
All right. There's some tape. Okay. I'll do it another time. I give up on this. All right, let's just finish off with the quiz, and then we'll call it an early day, and then we'll continue next time. Let me get some paper for the quiz.
I know what a hobby is. There was something that was like, yeah, it was like an American crisis all of a sudden. Yeah. Like all the market was going out. Everything, right? Yeah. Like all of
All right, the reaction is going to be hydrochloric acid with silver nitrate. I'll write it up on the board. Hydrochloric acid with silver nitrate. It's open everything. Yeah. Hello, Fred. You could even run to the library if you want. Start searching the books in the library. Just make sure you come back today.
Can we Google?
Stop though, you're going too far. And you have, yeah, what did you do? You already... Why is it so blue? Was there water left in there? Maybe some water. In fact, when you add the ethanol to the solution, or you added ethanol?
It was kind of hard.
You gotta redissolve it. Add water. Don't try to finish it all today. You have time.
So I just put water in it.
Pour out the ethanol. Wait. But just do that.
Yeah, I'll use that.
Otherwise, you're gonna miss this.
All right.
Even though we like
I thought you were listening to that stuff. You
you know, like you're finding that out. You have to write.
Make sure you write the complete equation, the ionic equation, and then ionic. Also, point out the driving force. Don't just say driving force. It's not specific enough. But, you know, if a gas formed, tell me what the gas is, or point to it and say gas formed, or anything else.
If you wouldn't specify before, did you want like...
You need an arrow to it, or if I wrote specify, you got to specify specifically what, what it is. I'll just put a watch glass over it and leave it in your drawer.
We had that discussion last time.
Were you right? Because you know, like, I'm pretty sure before. Yeah. You guys are deciding the final one. So maybe it's a battery break. So it's fun.
Yeah. So I go from song
Where do we place it? Here?
Yeah, right there.
Yeah, it is.
What's your gut feeling? I don't need this. Driving matters. Driving force. Oh, this is nice. How do you spell precipitate?
You can just put PPT and you have to put precipitate.
Mark off points, dude. Little man. See you guys next week.
Yeah. Later, man. Have a good weekend.
I'm so glad you got this. It's too easy now.
But I did it anyway.
That's for me.
Thank you. Oh,
Madden 09, man. Let's go.
It's too easy. Yeah, right? Maybe it's like a maybe. Hell yeah, maybe.
You can do both. Then you just go there.
Oh, yeah, yeah, that's great.
I got an email. I guess I'll buy it. And honestly, the calculator, you just.
Wait, where did you say?
What's the consensus so far?
I don't know. Yeah, like why did he do like the other one this week, the harder one this week, and the easier one?
Yeah.
This one was like
I think he just pulled it out of the chemical reaction
Like out of the
review
hat.
thing. It's like, yeah.
it's like oh, I guess we just.
Or do you see it?
The phone second lead.
Oh, so the ACO, so the ACO.
I'm just gonna write it.
No. Other Saturday. Other Saturday. I don't work Saturday. Alright, catch you later.
Oh, yeah, I heard you guys talking about physics the other day in the Mesa Center. Yeah, that sounds scary. Just do it.
And then we like do something.
Right? He just has a lot of trust in us. Chill. Bye, guys.